Well, first of all, thanks for coming to this public lecture series organized by the Hawaii Conservation Alliance. I'm very glad to be here, to speak to a group who cares about the conservation of our beautiful environment. So I think that this is a really good opportunity for me too. And I'll be talking about the precipitation extremes in the Hawaiian Islands under changing climate. This here is okay? Yeah, all right. And I cannot do this work all by myself, so I have some collaborators with Yan Qing. She was my former graduate student, and Chase Norton is my current graduate student. He couldn't come here because he said he needs to run work. He needs to do some, slave work. Okay. And then Tom Schrader, he was my colleague. He was retired, end of last year. So I'm from Department of Meteorology, and also I run the Hawaii State Climate Office from i-Manoa. Okay. Oops, there's another one. Oh, this one. Okay, this one. Yeah. So I need to hold this too. Okay. Okay. Outline of my talk. I have 3 parts. I will start with showing the trends in climate change indices. Okay. And then the second part is a projection of future heavy rainfall events for Oahu. Okay. And the last part, I will say a few words about the Hawaii State Climate Office, what kind of work we do. Anybody recognize this background? This background? Close. Norway, that's right, Norway, yeah. I was invited to give a talk last September in Norway, in Bergen, Norway, on the west side of Norway. And, we had this sightseeing, through the field. So my wife took these pictures, and I thought it was very nice. Okay. All right, if you are fortunate enough to live in Hawaii for a long time, you'll notice that heavy rainfall events are common. Okay, and this is mainly caused by the interactions of we call a synoptic system with local terrains, so resulting heavy rainfall event and cause damage to properties, to agricultural and roads and so on. Okay. And when I say the synoptic system in meteorology, we mean something like a cold front, okay, or something called a Kona storms. In winter we have a Kona storm, which brings lots of rainfall. Okay, and also sometimes we have this moving upper level trough or low level trough. Okay. And heavy rainfall events also cause environmental problems. Okay. Pollutants carried away by stream flow during heavy rainfall event are one of the major threats to nearshore marine ecosystem, particularly the coastal coral reefs. Okay, because we know that after heavy rainfall, if you have the chance to see the coast, it's all brownish looking. So the state always issue this kind of brown water advisory or warning. Sometimes the water becomes contaminated. It's very dangerous to go there. And during the last 8 years, we have some notable heavy rainfall events, starting with this Halloween flood of 2002 at the i-Manoa. The damage was around $80 million for US alone. Okay. And this picture shows the damage caused by this Halloween flood at the i-Manoa Hamilton Library basement. You can see all the original documents were damaged. Okay. And between February and early April of 2006, there were extensive flood events. Okay. And the Kaloko Dam on Kauai broke and killed 7 people, and costly litigations followed, involving the state and also the county and also the owner of the dam. Okay. And also for the first time, the Kahala Mall was flooded, and the movie theaters were closed for several months. So this picture shows the people are cleaning the Kahala Mall after the event. Okay. And 2 years later, in December 2008, there were also extensive flood on Kauai and Oahu. Damage was around 50 million. And there was a federal disaster declaration from the U.S. president. Okay. And more recently, in December 2010, okay, and we had a flood on Oahu and also on the Big Island. The Ala Moana shopping center was closed because of power outage by this rainwater. Okay. And the timing of this event was really bad because this occurred just prior to the Christmas break. Just a few days before Christmas. And we know this is the busiest time of the year. Okay. So since the center was closed, so it caused a lot of anxiety for the retailers in Ala Moana shopping center because they couldn't do any business. Okay. Okay, so on the other side of the coin, we also have a drought. Not only heavy rainfall, but also we have a drought. Okay. And drought in Hawaii is always a problem. And we know drought would reduce crop yield and also diminish livestock and also deplete groundwater supplies and also lead to forest fire and a brush fire. And here, this shows the drought history since 1980s, okay? Taken from the Hawaii Drought Monitor website managed by the DLNR. Like 1980 through 81, Hawaii and Maui County declared disaster. And then came 1982-83, El Nino, was a very strong El Nino, okay? Then this shows the lingering effect of El Nino, that the state declared disaster. Crop production reduced by 80% in some part of the Big Island. And then 1996 was another drought. Hawaii, Maui, and Molokai declared drought emergency, and the losses in agriculture and the cattle industry were around $9 million. Okay. Then there was another very strong El Nino in 97, 98. Okay. And then Hawaii and Maui declared the drought emergency, so there was also a big loss in the cattle industry. And 2000 to 2002, the governor proclaimed statewide drought emergency, and the Secretary of Interior designated all counties as primary disaster areas, and the statewide cattle losses were estimated at $9 million. Okay. And their list only goes to 2002, but that doesn't mean that there was no drought after 2002. And just yesterday, we're looking this another source. This is U.S. Drought Monitor. So they show the most recent drought conditions up to February 21st. So that was just last week. Okay. So this shows different degree of drought in the Hawaiian island. So except for Kauai, all other islands shows very bad drought conditions, particularly for West Molokai, Lanai, and also southern part of Maui, and also the western part of the Big Island. Here shows that the drought was extreme here, okay, very extreme. Okay, now I move to the first part of talk is trends in climate change indices. But before talking about that, let me first show you this time series of HRI anomalies. So this is the long-term winter rainfall. Winter means from November through March. Okay. In Hawaii from 1905, so almost from the beginning of the last century to 2009. Okay. So because we know winter is the rainy season. Okay. Okay. So this is so rainy season for Hawaii. And here HRI means the Hawaii Rainfall Index, so which is derived from 9 stations from each of 3 islands, Kauai, Oahu, and the Big Island. So for each island, 3 stations are selected on the windward side, 3 stations selected on the leeward side, and 3 stations selected between windward and leeward. And also on each side of the island, stations are selected from low to high elevation. Okay. So altogether, we have 27 stations. Okay. come altogether from these 3 islands. So they represent the rainfall variations at a different elevation, because we know in Hawaii, elevation is important, as far as the rainfall gradient is concerned. And also they represent the rainfall variation with respect to the direction of the prevailing northeast trade. So that's why we choose a station on windward side, station on leeward side, to trying to get an even distributions for all the islands. And the original rainfall data are standardized so that the HRI is a dimensionless quantity. There's no dimension. Okay. So in this diagram, this broken line represents the 0 values. So when values above this, it means you have a more rainfall. When value below 0 means you have a below than normal rainfall. And also shown here is that this a solid line, okay, which represents the long-term trend in rainfall, okay, over the last 1 to 5 years. Okay. So what we see here is very clearly there is a long-term downward trend over the last 1 to 5 years. So in other words, we are getting less and less rainfall. Okay. And also another information is that we see, since 1970s, we have a lot of years with low rainfall, right? Okay. So this because there's a major climate shift occurred in 1970s in the Pacific Ocean. So since then, we see a lot of low rainfall years. And also shown here is that I just include the 2 El Nino year. This is the 82, 83 El Nino. Rainfall was very low, and another 1997, 98 El Nino rainfall also was very low. Okay. Because if you remember previously, I talked about a drought history that some El Nino years then we have a drought. Okay. So this to show the relationship between El Nino and the Hawaii rainfall. Okay. And we know El Nino usually kicks in maybe in spring or summer, and then it runs through about 1 year, then it disappears by the next spring or summer. Okay. So here, year 0 indicates the time when El Nino develops, and the year +1 means the year immediately after year 0. Okay, right. And this is just for the abbreviation for seasons: spring, summer, fall, and winter, and so on. Okay. So during the El Nino developing year, that we see actually rainfall was slightly above normal in Hawaii. Okay. So this is based on this 27 stations, as I said before. Okay. But this changes quickly from fall to winter. Then we see winter of the year +1, that the rainfall becomes very low. Okay. And there's a large negative anomalies. And these large negative anomalies persist through spring, year +0. Even by fall, year +1, that the rainfall was still slightly below normal. Okay. And the numbers here is also of interest because it indicates the number of total seasons with a negative rainfall index during 20 El Nino events. So in other words, 18 means 18 out of 20 El Nino winters are marked by low winter rainfall here. So in other words, there's 90% chance that the winter year +1 would be low rainfall, okay, would be drought. And the chance for spring year +1 is 80%. Okay, right. And we know that the bulk of annual rainfall in Hawaii comes in winter and spring. Okay. And the large negative anomalies for these 2 seasons and also the high frequency of low rainfall occurrence are a robust indicator of water shortage for the year following El Nino. Because El Nino usually occurs in spring or summer, then if it is developed this time of the year, then there's a good chance the following year will be dry for Hawaii. This is the rainy season in Hawaii. Okay, come back to the trend in climate change indices. This is the figure that we saw before, but this is based on the winter rainfall, right? 5 months winter rainfall. The next question is that how was the change? Oh yeah, thanks. Yeah. In precipitation extremes, will there be similar or different, from the total winter rainfall? Okay. And also another question is that how was the change, from one island to another? Because the HRI, Hawaii Rainfall Index, is based on the average of 3 islands, Kauai, Oahu, and the Big Island. But that doesn't mean that all the islands will be the same. Okay. Sometimes as I will show you later on, we do see some regional patterns. Okay, to look for the climate change indices, we use the definition from the World Meteorological Organization. WMO means World Meteorological Organization. Okay. And we use the first index is called SDII, which means Simple Daily Intensity Index. That is the average precipitation intensity in wet days. So suppose, this year we have 100 days with rainfall out of 365 days. Then we just sum up all this rainfall during these 100 days, then divide it by 100. Okay. So the unit of SDII would be millimeter per day. Okay, millimeter per day. So this is the rainfall intensity. And R25 means annual total number of days with daily rainfall greater than 1 inch. Okay. So this is a unit is days. How many days you have more than 1 inch for daily rainfall? Okay. So this year could be 70 days. Next year could be 80 days. So and so on. Okay. And then the third one is R5D, which describes the annual maximum consecutive 5-day precipitation total. Because for meteorologists, we have something called a synoptic event, like a cold front, those kind of things. And usually, on average, their lifetime is about 5 days. So we can also look this 5-day rainfall total, okay, to see if there's any change. And the unit here is millimeter. Okay. And let's skip R95 because this needs more explanation. And go to the CDD. CDD means consecutive dry days. Consecutive dry days. Okay. So this is the annual maximum number of consecutive dry days. How many days there's no precipitation continuously? Okay. So that the unit here is days. Okay. And the first 4 indices are related to the wetness, conditions. And CDD defines the duration of excessive dryness, like how many days there's no precipitation continuously. Okay, we have about 60 years of data to see the difference in precipitation characteristics, and the data is first is split into 2 epochs, from 1950 to 79, and the second epoch is from 1980 to 2007, almost 30 years for each epoch. Okay. And this shows the PDF of SDII, which means Simple Daily Intensity Index. That's the precipitation intensity. Okay, so millimeter per day is the unit, and this is a PDF, means the probability density function PDF. Okay. So shown here are 2 curves. The broken line represents the precipitation intensity during this period from 1950 through 79, and the solid lines is for this period, 1980 to 2007. So what we see is that there is a shift in the peak distribution from the early epoch to the later epoch, right? Okay. So in other words, that the frequency of precipitation intensity near the peak distribution has decreased with time. Okay. And this is also can be supported from the table below. So from empirical data, the precipitation intensity can be classified into 3 groups called the light intensity, which means precipitation is less than 10 millimeter per day, just like today, it's light precipitation day. Okay. And then the second group is the moderate intensity, so it's between 10 to 15 millimeter per day, and anything higher than 15 millimeter per day we call the high intensity. Okay. So this table shows the percentage of each group for 2 epochs. Okay. So what we see here is that there is a decrease in moderate and high intensity from the first to the second epoch, and there's a corresponding increase in light intensity from the first to the second epoch. Okay. So this is basically consistent with this picture. Then we can also look at the PDF of consecutive dry days for these 2 epochs. So basically the peak distribution is around 9 to 11 days, no precipitation. Okay. But another interesting feature is that one can see there's a increase on the right tail of the distribution from the first to the second epoch. So in other words, that 35 to 80 consecutive dry days occur more often in the last 3 decades. In other words, consecutive dry days near the 35 to 80 days window occurring more often since 1980s. So this is probably not a good sign because we're getting longer dry days. Okay, after seeing the PDF, then we can look at the trend. Okay. So we use what is called the man candle method with the SINS method. We call the MKS method to investigate trend in precipitation extreme. So basically looking this precipitation intensity, 5-day rainfall total, consecutive dry day, and so on. Okay. And this method is a robust trend detection method. Okay. So I just skipped the details. Oops. This one really cuts up to some extent. Okay. So this one shows trend, spatial patterns of trend from 1950s to 2007, because this is a time when most stations start to have observations. Okay. And triangle, when triangle pointing upward means you have an upward trend. Okay. When triangle pointing downward means you have a downward trend. And if the triangle is a black, which means that the trend is statistically significant. Okay. When there's no shading, means that it is not significant. Okay. So that let's first look at this SDRI, which describes rainfall intensity. Okay. And we found that for most stations on Kauai that we have this downward trend, but none of them are statistically significant. Okay. And for Oahu, that again, this downward trend prevails. So this means that rainfall became less intense since 1950s for both Kauai and Oahu. And then when you look at Maui, you find some station shows upward trend, some station shows downward trend. Not clear. Okay? There's no clear patterns. Okay? And for the Big Island, we saw that this upward trend prevails. So this is different from Kauai and Oahu. So in other words, for the Big Island, that the rainfall became more intense since 1950s. Okay. So we do see some east-west difference in rainfall intensity. Okay. Because the Big Island is on the east, Kauai and Oahu are on the west. Okay. So this is for the rainfall intensity. We can also look at other indices such as R25, which defines the total number of days with daily rainfall greater than 1 inch. Okay. Then you can also see that you have a downward trend for Kauai and for Oahu. And for R5D, which means consecutive 5-day rainfall totals, that we found that the patterns is very similar to SDRI in the sense that downward trend prevails for Kauai, for Oahu, and upward trend prevails for the Big Island. Okay. And for CDD, there's a consecutive dry days that most stations shows upward trend. Okay. So that this means most islands shows longer consecutive period of no precipitation days since 1950s. So that's not a good sign. Okay. Okay, now come to the summary for part 1. So we're looking this trend of climate change indicators over the last 60 years, and we do see some regional patterns. Oahu and Kauai are dominated by this long-term downward trend for precipitation-related indices, but the Big Island shows just the opposite. Okay, they have an upward trend. Okay, so that for Big Island means more intense rainfall, more 5-day rainfall total, and so on. Okay, right. So we do see some east-west difference, some regional patterns. Okay. But when it comes to the drought, indicator CDD, consecutive dry days, we see there are upward trend everywhere. Okay, for all the major islands. So this means we have a longer consecutive dry days since 1950s. Okay. So this is for all the islands. But for precipitation intensity and other index, there's regional patterns. Okay, now moving to the second part, is estimating future heavy rainfall events for Oahu. The first part of my talk was based on the present day observations. Okay, but we are also interested in knowing future variations for various purposes, for planning or policy analysis and so on. Okay, and for projecting future variations, a standard tool is to use the GCM. GCM stands for General Circulation Model, okay, which simulates the physical process of the ocean and the atmosphere. You need to give some initial condition, boundary conditions. Okay. And GCM is based on the mathematics and also the law of physics to describe the behavior of the climate. And GCM also represents the atmosphere and the ocean by dividing it up into great square. And for GCM, the horizontal grade spacing is very coarse. So this presents a problem for Hawaii because of the small size of the island. In other words, the GCM presents the entire Hawaii islands as a single great box. Okay. So in other words, that we know we have this windward, leeward difference, and so the GCM cannot resolve this kind of features, or even cannot resolve difference between Kauai and the Big Island. Okay. So in other words, that the GCM cannot show this microclimate in Hawaii. So without further analysis, the predicted change from GCM are not very useful. Okay. So we need to downscale simulation from GCM for Hawaii. And what is that downscaling? That's the process for making a link between large scale atmospheric circulation from GCM and local rainfall, like Honolulu. And basically, there are two approaches for downscaling. The first one is the statistical downscaling, is to find an empirical relation between circulation and local rainfall using some kind of statistical method. So that's called a statistical downscaling. And I will give examples on this shortly. Okay. And the second approach is dynamical downscaling. That's to obtain high-resolution climate information from GCM. So this is achieved by using a high-resolution regional climate model that is initialized with output from GCM. So this approach is more desirable because it gives you, physically consistent features. Okay. But the downside is it is computational demanding. Okay. Takes a lot of time and also a lot of skill. And currently, we have a project funded by Kauai County to provide a high-resolution climate information for Kauai for the next 50 years. Okay. High resolution means at 1 kilometer resolution. Okay, just say a few words about the statistical downscaling. That's the work that Chase Norton and we did recently. Is that what we did was we first looked for rainfall station data. So we need about 30 years of data, daily data, because for statistical work you need to have a large sample size to yield stable results. Okay. Then after some quality control, only 16 stations for Oahu during this period are used, okay? Because we have a lot of stations, but we have a lot of stations with missing observations, okay? And then for the GCM data, we have a 24 GCM available, but it's impractical and also inefficient to downscale each of GCM for use because of the huge amount of climate data. Okay? So we need to find which GCM is most representative for climate in Hawaii. And we used two tests. The first one is called the baseline test, which compared the average observed rainfall during this period, last 30 years, with the GCM projections, okay, of the same period. And then we rank these 24 GCMs, okay, based on the absolute difference. And then we also look for the future projection test. So we compare each GCM to filter out outliers, okay, and then rank them again. Okay. So through these two tests, okay, then we try to find the overall high-ranked model among 24 GCM, and turns out that ACOM 5 A2 is best for us. And for the statistical model, we use a neural network because it is a nonlinear method. Because when we deal with a heavy rainfall event here is defined as values greater than the 90th percentile. Okay. So in other words, we're looking at the top 10%, okay, of rainfall. So this may not respond linearly to the atmosphere forcing. So we use a nonlinear method. And also the advantage of neural network is it can find the maximal correlation between predictors and the local rainfall. So here we choose 4 predictors like low level wind, zonal wind, meridional wind, sea level pressure, and also relative humidity in the lower atmosphere. So only 7 stations shows a correlation. So this reduces from initially we chose 16 stations, but now down to 7 stations. And this figure shows the location of these 7 stations from Campbell, Honolulu Observatory, Honolulu Airport, Punch Bowl to Pecos Drive in Hawaii. So this is all the leeward stations, and we have 2 windward stations, Pali Golf Course and the Waimanalo Farm. Okay, 7 stations. So this figure shows the number of heavy rainfall events, okay, for these 5 leeward stations. Okay. And for each station, I have 3 different color bars. The blue one shows the observed heavy rainfall event during this 30 years, from 1979 to 2008. And the red one shows for the same period, this is from the GCM, okay. Because this one basically to show that how GCM can simulate the present day climate. Okay. If the simulation is good, then this gives you confidence. If simulation is lousy, then probably you cannot trust too much. It's future projections. And the green one shows the GCM projection for the future, for the next 30 years, 2011 to 2040. Okay, take a Honolulu International Airport as an example. Okay. During this period, 1979 to 2008, 47 heavy rainfall events occurred. Okay. 47. And the GCM for the same period shows 43 heavy rainfall events. So in other words, the GCM slightly underestimates the frequency of heavy rainfall event under the present day climate. So I call this the present day climate. Okay. And for the future, for the next 30 years, that the GCM suggests we have 57 heavy rainfall event. So this is more than the current heavy rainfall event based on the actual observations. And this is not only for the Honolulu Airport, this is also found for other 4 leeward stations. So when you compare the blue one with the green one is always larger than the blue one. Okay, right. So in other words, more heavy rainfall events are projected in the future. Okay, right. On the leeward side of Oahu. So this is for the frequency of heavy rainfall event. And you can also look at the intensity of heavy rainfall event to see whether heavy rainfall event will become even heavier, okay, or become less heavier. And this shows that, again, taking Honolulu Airport as an example, according to the current observations from the actual data, that the average rainfall, heavy rainfall intensity is 79 millimeter per day. Okay, so this is a slightly over 3 inches per day. That's a lot of rain. Okay. And for the same time period, the GCM shows 73 millimeter per day average intensity. So in other words, the GCM shows a slightly dry bias, okay? Because ideally this value should be equal to the simulation. That would be the best, okay? But we know this never occurs. Okay? And for the future, that the GCM simulation shows that the average intensity is reduced to only 64 millimeter per day. Okay, right. So this also shows for all other stations. Okay. Now the green one is always smaller than the blue one. Okay, right. So that the projected average precipitation heavy rainfall intensity is lower than those from the actual observations and also from the model simulations under the present day climate. Okay. So summary for part 2 is that here we use a neural network to do the downscaling of daily extreme precipitation event for Oahu from GCM output and also projected into the next 30 years. And we found that there's an increased frequency of heavy rainfall event, but the average intensity is decreased, okay, for the southern shoreline of Oahu, including Waikiki, for the next 30 years. So that's our findings. Okay, now move to the last part of my talk is Hawaii State Climate Office, HSCO, which is housed in the Department of Meteorology, okay, at the i-Manoa. And this is our email address, okay, hclimate. And I have Chris here. He is mainly, responsible for the, for this climate office. He and also the Chase Norton, okay. And we were, recognized by the AASC, American Association of State Climatologists, in 2002, because each state is supposed to have one state climate office, and AASC is a national organization. So, okay. So every year we have to write an annual report, and we have to pay our membership due, okay, to be recognized by the AASC. And we are also in partnership with NOAA, National Climatic Data Center, and also with regional climate centers. There are 6 regional climate centers in the country. And we serve as an official clearinghouse for climate and weather records in Hawaii and also U.S. affiliated Pacific Islands such as Guam, American Samoa, Marshall Islands, and so on. Okay. So we keep the original climate data in Hawaii. We have some handwritten record back to 1940s, 30s, even 1920s. Okay. Those handwritten records. Okay. Sometimes it's very difficult to read. Okay. And we also provide climate data to users on a timely basis. Actually, this is our main function. Okay. And the users include civil and environmental engineer, planners, insurance company, government agencies such as Department of Health, Honolulu Police Department. Sometimes we have a case involving accident, and police needs to know the weather at that particular time, particular spot. Okay. For example, at the intersections of Kapiolani and Kalakaua and so on. Okay. Right. And sometimes, there was a cold case that the police wants to know, what happened with the weather on that particular day. Okay. And researchers, students, and individuals. And we also provide current emerging news to TV, newspaper, and radio. In October last year, I was interviewed by the Hawaii Public Radio. And Chase Norton and I also were interviewed by the KGMB TV stations last October about this changing rainfall events in Hawaii. And we also do consulting service. There was a big rainstorm flooding in January 2022 at the Manali Bay on Lanai, and we were asked to provide a return period of this rainstorm using the current data, current technology. And this shows some project that we have been doing, the drought risk assessment GIS mapping for the Hawaii Island, funded by DL and Kona Coffee and the climate, funded by NOAA, because the coffee bean growing season is highly dependent on temperature and the precipitation at certain time of the year. So that coffee growers, they need to know climate variability and climate change in Kona area, because Kona is not very big, but they have over 600 coffee farms. They have a lot of coffee farms over there. Okay, so there's a big interest in knowing the climate in that regions. So we were asked to provide high resolution climate information for that area. And then we also provided data to update rainfall frequency atlas for Hawaii by NOAA, funded by Department of Health, and also for the looking for monitoring climate for the Pacific Island, funded by National Park Service, and also updating rainfall index, rainfall station index and atlas for funded by 4 counties in Hawaii. Okay. This is the references of my talk. And actually, I brought some copies of these papers with me. If interested, please take one, and they are free. Okay, free. And you can also download these papers from the Hawaii State Climate Office website. So just Google the Hawaii State Climate Office and click State Climatologist button, and then publication. Then you can find publications, all in PDF. Okay, I think I stop here. Okay, thank you.